Hello and welcome. Today we're going to be talking about integration using partial fractions. Partial fractions is yet another pretty useful integration trick. But I'd have to say it's really just an algebraic manipulation of the integrand. There's no actual calculus involved here. You're simply doing algebra to simplify an expression, to break a big expression up. You take an f of x dx that you want to integrate, and you take f, which is some sort of complicated thing, and then what you try to do is take f of x and turn it into g of x plus h of x plus q of x plus p of x, so on, some number of terms where each of these is simple to integrate. All right, so whether it's calculus or just an algebra manipulation, it doesn't matter. The point is we have an integral that we need to calculate, and what we're going to do is, of course, try to find a way to break down this integrand into smaller, more bite-sized pieces, if you will, that we can then integrate easily. But the question then, of course, is, well, what is f that we're talking about, and how do we break it down? So the type of f's that this works with is if f is a rational expression or a rational function. So what's a rational function? Of course, it's going to be a polynomial on top over a polynomial on the bottom. Okay, the one proviso here is, I'd say, what you want to make sure, of course, is that the highest power is in the denominator. So by highest power, I mean x to the n, whatever that is, n, in the denominator. If not, you should go simplify it by doing some sort of polynomial division, and we won't go into that. We'll just, most of the time though, it's very clear that the issue will be in the highest power will be in the denominator. Okay, so let's just give an example. A simple example, of course, is 1 over, we'll try x squared minus 1. All right, so clearly this checks out here. 1 over x squared minus 1 certainly has a higher power. The question then is, of course, we want to integrate this function. So this is familiar. This does look somewhat familiar because we know that 1 over x squared plus 1 dx has an easy antiderivative, tangent inverse of x. But this function, nope, we don't have a nice antiderivative just calling us out that we can use. But it turns out there is a way of simplifying 1 over x squared minus 1. And it comes from an idea that I think in algebra, a lot of people, when you're taking an algebra class, one of the first things you do is combining two rational expressions together. What we're going to do is actually break this up into simpler So we're going to break this rational expression up into simpler rational functions. And in doing so, what we're going to try to do is utilize a neat property. It will be able to recognize these simpler ones, and the idea is that these simpler ones, of course, will have easy antiderivatives. Okay, right, so let's just go on and carry through this example. Let's notice a few things about this expression, this example that we're looking at, is that I can't factor it. It is actually a difference of squares. So, oops, it has that factorization. So you may know from studying many rational expressions that they're often, we can break this into two rational expressions of a lower power. What we notice about this, of course, is this is going to be an x squared. There's an x squared there. But if we break it into two rational expressions, we should be able to break it into its binomial parts, like this. But I'm going to put an a there that's an unknown a, and another constant b that's an unknown constant there, x minus 1 here for that binomial, right? And so often in your algebra class, you were asked to combine these together. And that you do that, of course, by finding that common denominator. What we're going to be doing is going the opposite direction. We're starting up here with our combined rational expression. And what we're going to do is try to take it apart into two simpler pieces. What's important about this, though, so the goal then is to find constants a and b that makes this work. Okay, well, let's see if we can find those constants. Just like before, what we can do, though, is say that, well, okay, if I have 1 over x squared minus 1, and that's equal to 1 over x plus 1 times x minus 1, and that's equal to a over x plus 1 plus b over x minus 1, and a and b are unknowns. But what we do know about this is this equality right here has to be true for all x values. Okay, and so it has to be true for all x values, and I should make a proviso. It has to be true for all x values in the domain. But we can even kind of, we'll see that we can even push the edge of that. It has to be true uniformly for all these x values that are in the domain. And so it should even needs to be in the limit as x goes to closer and closer to the division by 0 points in this function, in fact. So what we want to do then is see if we can isolate these a's and b's there and see if we can figure out what they are. What I can do then, of course, if we set this equation, if these two expressions are equal to each other, what we want to do then is see if we can kind of solve for a and b. So what we're going to do is we're going to multiply the whole thing by x plus 1 and x minus 1. And in doing so, okay, we're going to distribute it into all these terms. And we're even going to distribute it into that term on the other side. And we end up with, of course, 1 is equal to a times x plus 1 times x minus 1 all over x plus 1 plus b over x minus 1 times x plus 1 times x minus 1. Now, clearly, we can cancel those, and we can cancel those there. And on the other side, they both cancel as well. I didn't do that side, but I hope you caught that. And now what we have here is a times x minus 1 plus b times x plus 1. Right, this equation that we obtained from above, but now we've manipulated it to be this new equation here. What's useful about this now is that, of course, we should be able to, again, I need to just state this, that this is true for all x's. And what that means then is, so it must be true for particular x's. And so we can actually choose some good ones. If you're looking at this equation, think for a second. You can pause the video and ask yourself what might be some good x's to plug in here that would help us solve for a and b. Right, I'll give you a few seconds to think about x values that might help you solve for a and b. So right now we have two unknowns. We have an a and a b that are both unknown. Is there a way to make this problem simple so that you can solve for a and b independent of each other? All right, well, I hope you've guessed it. If not, let me just show you where we're going with this. Let's actually choose x is equal to 1. I'm choosing that because when I plug it into here, of course, I get a times 0. We get 1 is equal to a times 0 plus b times 1 plus 1. And that whole equation then becomes 1 is equal to b times 2. Otherwise, we say b is equal to 1/2. Right, so by choosing the right x value, we're able to eliminate one of our unknowns from the problem and find the other one all by itself. Right, so now we can choose a different x value. And now I'm betting you can guess a lot clearer what x value would be good. I'm actually going to choose x equals -1. Of course, then I'm going to get a 1 is equal to a times -2, because I'm plugging in the value of x equals -1 to the equation, plus b times 0. Of course, that goes away. And what I'm left with then is that a is equal to -1/2. Okay, so again, we haven't done any calculus yet, but let's see where this gets us. I'm going to go to the next page now and write down our problem as we had it before. So now we had the integral of 1 over x squared minus 1 dx, but then we decided to write it this way as a over, back up, let me make sure I get this correct, a over x plus 1 plus b over x minus 1 dx. And again, now these are the identical integral. We've just broken up algebraically our expression into two smaller expressions. And now we found those a values. So the a value is going to be -1/2 all over x plus 1 plus, and then we have a positive 1/2 here over x minus 1 dx. So now what I'll do is bring the -1/2 out front there. And do the integral here, 1 over x minus 1 dx. So now we ask the question, have we simplified our problem? Well, let's see if we can think about it this way. I'm actually going to do a u substitution. I bet some of you don't need to do this substitution, but I think it's helpful, clarifying to see that if that's an x plus 1, I let that equal to be u, then of course we're going to get du dx is equal to 1, in which case we get -1/2 is equal to the integral of 1 over u du minus 1 over 2 integral. And now I'll do a different u substitution here. Let u equal to x minus 1. Du dx is equal to 1 again. And we're going to get 1 over u. You know, maybe it's I'm going to even be a little bit more cautious here and call this w as a different substitution, just to contrast and just to make sure we know to keep the two separate. All right, and so now the integrals here are very clear at what we want to get out of this thing. Sorry, we need to put a plus sign there. That was a mistake. All right, so now we have a negative 1/2. And the antiderivative of 1 over u, of course, is natural log of u. But that becomes this. And that becomes natural log of x minus 1. And now we can add a plus c there. All right, so that's our final answer, and that's what partial fractions allows us to do. We can go a little bit further here. So remember, this is the integral of 1 over x squared plus 1 dx. And then we can do this. We have those natural logs, and we actually have a difference of natural logs. We can combine them up just to give them one compact expression. So there's a 1/2 out front, and then what we get here is an x minus 1 over x plus 1, all absolute value, plus c. So that would be the most compact way of writing it, but this way up here is totally fine as well, and one or the other may be more useful to you in some application. Okay, well, I hope that helped show you a simple example. I'd like to do now one that's a little bit more complicated. First, though, I do want to note there's another important integral that we should probably kind of spend some time with, which is this integral here, 1 over x squared plus a squared dx. Okay, so this right here is not factorable into real binomial factors. Okay, there's no way I can write it as, x squared plus a squared. This is a sum of squares, not a difference of squares. So there's no way I can write it as, x minus c, c1, x plus c2, like that. That's just not going to be possible at all. But what we can use is something else that might help us here, is to note that the integral of 1 over x squared plus 1, as we had noted earlier, equals the inverse tangent of x. Right, so what we can do with our problem now with this new constant, where now a could be any real number, okay? Except for it shouldn't be 0, obviously. Otherwise, I think we could solve this one through other means. But what we can do is, now what I'm going to do is I'm actually going to factor out the a squared. Like that. Right, so the 1 over a squared can come out of the integral. And now, if I look at this term, I can actually, of course, put the a inside the square like this. And then, of course, I can let u equal x over a. Du dx is going to be 1 over a. Another way to write this, of course, is that a times du is equal to dx. Well, if I put that all together, then I'm going to get a over a squared, the integral of 1 over u squared plus 1 du, or 1 over a, integral of 1 over u squared plus 1 du. And now we can factor this all. We can do the antiderivative now very simply. And I can resubstitute back in x and get an x over a in its place plus c. Right, so that formula will become important if you have a non-factorable, or what we call, this is also called a irreducible quadratic. So the only roots that it have are pure imaginary roots. Okay. So what we want to do in this case, so now I want to look at another problem that might be kind of interesting for us. Now let's like tackle a problem where we're going to use our partial fractions in a really involved way with a more complicated expression that we haven't seen yet. So what I'm going to do is the integral from 5x minus 4 all over 2x squared plus x minus 1 dx. Right, so before we even start with the integral, I think it's probably worthwhile to see if we can factor that bottom. And so we're going to need to have a 2x in one of them and an x in the other, most likely. And let's see if we can have those in there. Can we figure out what we need? We need to have a 1 here and a 1 there, but now we have to figure out which sign. We need one of them to be positive and the other to be negative. The best way to look at this is just to try to guess. Let's see if I put a negative here and a positive there, that should work out, and that in fact does. I can even write down 2x squared plus 2x minus x minus 1. Yeah, that checks out. Okay, good. All right, so here's my two binomials. Right, so now, of course, I can write it as 5x minus 4 all over 2x minus 1 times x plus 1. And now I'm going to write it as, I'm going to break it up into those two rational expressions with x to a lower power than x squared. So now we're going to have 2x minus 1 and an x minus, or x plus 1 right there. So again, we don't know what a and b are, but we assume that those two a and b must exist in order to solve this problem. All right, let's see if we can do another example here with this. So just as before, let's multiply everything by 2x minus 1 times x plus 1. And then we're going to get a 5x minus 4 is equal to a times x plus 1 plus b times 2x minus 1. All right, and then we're going to I'm going to choose x to be some convenient value. Again, pause and ask yourself what x value would be most convenient. All right, if you've made your choice, I'm going to choose x equals negative 1. I think that will be a nice, easy value. And of course, when we do it, we have to plug that in everywhere because, again, this equation is satisfied for all x. So, again, pick one. Pick any one, and it'll work out. So, of course, we have a negative 5 minus 4 is equal to 0 times a, I should say, times b times negative 2 minus 1. We can do a little simplification here. That's a negative 9 is equal to negative 3 times b, otherwise known as b is going to be equal to 9 over 3. is equal to 3. All right, we found the b value. Now let's go find the a value. So to do that, let's choose x to be equal to, I'm going to say 1/2. I'm going to choose 1/2 because it's going to eliminate the b parameter from my problem. So I'm going to have 5/2 minus 4, that is the left-hand side of the equation, is equal to a times 1/2 plus 1 plus b times 0. All right. This one should be fairly straightforward to do. We have to do a little bit of fractions here, but maybe not that much. So we have 5/2 minus 8/2, and that's going to be equal to minus 3/2, and that's going to be equal to a times 3/2. So a is going to be equal to -1. All right, so we found our a and we found our b. Now let's go back to our original problem. I had the integral of 5x minus 4 all over 2x squared plus x minus 1 dx, which is now going to be expressed as minus 1 over 2x minus 1 plus 3 over x plus 1. It's important to remember that you have to remember which constant was associated with which denominator in order to apply them correctly at the end. Otherwise, of course, you won't get the right answer. However you choose it to begin with, you have to remember that in the end. Right? So for this problem, we can always break it up into two smaller integrals, bring the constants out front. Okay. For this one, though, I see I'm gonna let u equal 2x minus 1. du dx is going to be equal to 2. And that means, of course, that du over 2 is equal to dx. That's going to help us write it this way. And this one I should be able to anti-differentiate straight away. Like that. And that would be a good final answer. All right. All right, so those are two examples of basic partial fraction style problems. In another video, I'm going to show more challenging examples and what to do when you have maybe a cubic in the denominator or some other more complicated expression. There are other ways. Essentially, you're just going to have more terms. But we'll talk about that in a later video. I hope this just gets you started in your adventures with partial fractions.